Noah.
Just try. Giansiracusa. I knew you were going to get it.
He's going to be talking about persistent homology machine learning for fingerprint classification.
All right, well, thanks for the invitation. So just to kind of set the motivation for this, we weren't trying to go out and beat the state of the art for fingerprint classification. There's a lot of fantastic results in engineering, things that are used. Even when you take your phone, there's algorithms that are doing that. So we weren't trying to use TDA to supplant those. We just thought this is kind of a fun data set and classification problem where we might gain a little bit of insight into what TDA sees and how it sees it, specifically persistent homology. So we know the definition of persistent homology, but in practice, barcodes are very, very complicated, much more than that sort of Klein-Bottom model we saw with the natural image statistics that Gunnar showed. So every time I tried persistent homology, the barcodes look kind of like a mess. And there's still a ton of signal in there, but we were kind of curious, what is it picking up in some concrete settings? So that's sort of why we thought to play with fingerprints. Okay, so just to set the stage for the classification problem, this basic classification of fingerprints goes back to Sir Francis Galton, who was Charles Darwin's cousin and also the inventor of the statistical notion of correlation. So he kind of launched the field of fingerprints, although even going back thousands of years, there's examples of pottery that has fingerprints that were used for identification. So it's a long history and became sort of more mathematical as things proceeded. So the basic story, and this is fun, you can look at your fingerprints either during the talk or afterwards, is you can largely think of fingerprints, and you actually have this for all digits of your fingers and not just the thumb. It's a little blurry to see here, but you can kind of Google and see these images. Roughly they fall into these things called arches, loops, and whorls. I can't really see on this projector image, but if you just Google image for fingerprint types, you'll see these. So it's kind of fun. It's a little hard to see, but you can look at your fingerprints and classify all of this. So it's easy to do, by hand as a human expert, and of course the idea is you want to automate this. So one of the main things that people use for fingerprints, it's actually not really used so much for classification, it's used for comparison. So if I swipe my fingerprint twice on my phone and I want to figure out that the image is not exactly the same when it's the same person, it uses these points that I'll talk about in a second. And also if I want to compare two people's fingerprints and say, oh, they're probably from different people, most, not all, but the majority of algorithms are based on what are called minutia points. So this is zooming in your fingerprint. The lines that you see on the fingerprint are called the ridges, so they form a ridge pattern. And the sort of macro or global geometry are these things, the loop, whorl, and arch. But if you really zoom in, the kind of local geometry is that these ridge lines, they terminate and bifurcate. So I forget which of the light and the dark is the bumped up ridge versus the indentation, it doesn't really matter. But as you follow a ridge, sometimes one will split and sometimes one will terminate. So you actually can mark these points where these bifurcations and terminations happen. And moreover, not only can you mark where they happen, that's the coordinates to the minutia point, but there's also an orientation, an angle at which these two phenomena occur. So again, the majority of algorithms, though not all, but something like 50 or 60%, for comparing two different fingerprints, for measuring similarity, does just use these minutiae. So it strips away all information of your fingerprint, just looks at the location of these. Classification, in fact, I didn't find a single example in the literature of using the minutia points for classification, meaning deciding if each fingerprint's a loop, arch, or whorl. And I even found a survey article that says minutia are not useful for that. So of course, two things popped in my head. Is one, I'd love to prove them wrong because my training as a mathematician, and I'd love to see statements that sound like a theorem and try to find counterexamples. But even more naively than that, a fingerprint really is a point cloud, right? It's this collection of minutia points. So if you realize in the literature that fingerprints are viewed as point clouds, how could you not want to try to apply persistent homology? So that's basically what we did, is we said, let's try persistent homology. Okay, so let me just go through this quickly. It's hard to read the details, but the basic idea is we need to record the fingerprint minutia points. So we used an FBI database that had these manually extracted by experts. It was a small database of something like 250 fingerprint images, but each one an expert identified the type, located the minutia points, found the angles, all that stuff. So we have locations and angles, but we still need a metric, right? When you do persistent homology, you need a point cloud in a vector space. So the first thing you can do is just work in R2, where you have an x and a y coordinate. But we also want to work with the orientation, so I can really think I'm on this sort of generalized cylinder where I have the x y, and the angle, the orientation of the minutia point. Well, now you have to choose a metric, so there's various ways of combining these things, but basically you can choose various like LP norms on the Euclidean space, and you can choose various LP ways of combining. There's kind of one standard norm on the circle, which is just take radian measure, but then you have to figure out how to combine these. So we just kind of randomly, this wasn't done in an intelligent, fancy way, we just randomly threw down a bunch of various LP norms. Yeah, not too much to say about that. Okay, so this is zooming in, this is a better picture, we can see these. So both to sort of cheat a little bit and because we know TDA, one of the beautiful things about TDA is you don't have to worry about orientation, right? If I take an image and I rotate it, or if I flip it around, the topology doesn't change. That's really good for fingerprints because one of the annoying problems people deal with is, you know, if the FBI images your fingerprint and then they do it again and it's slightly rotated, you really don't want to see that distinction. So that's the good news, is that topology automatically is, you know, non-coordinate based. The one downside is people do, in fingerprint community, do like to distinguish between a left whirl and a right whirl. And unless you go out of your way to encode that, almost any topological measure you find is not going to see the difference between left and right. You could sort of slant these things and break the symmetry, but we just sort of cheated. The database was small, so we just lumped left and right arches into one category, the whirls, which I think are the prettiest, into one category, and the loops. And notice why it's a little hard to see in the picture, but the arches and the loops don't have such a striking distinction. They are different types, but the whirl really looks kind of geometrically very different than the others. Okay, so here's just a little pictures of what the minutia points look like. So these fingerprints roughly had about 100, maybe 80, I think it ranged from like 60 to 120 minutia points identified. And these are plots where we have the x-coordinate, the y-coordinate, and the z-axis, the vertical here is the orientation. So you really need to identify the bottom of these cubes with the top of these cubes, because this is 0 degrees, this is 360 degrees. So it looks a little bit noisy, but if you have this in a software program where you can kind of rotate the image and see the 3D better, especially in this example, you can kind of see that there's sort of a helix structure. So the points, as your z-coordinate is moving, the points kind of wrap around. I saw this in some of the fingerprint types much more than others. So for instance, the whirls, I didn't see it, but both the loops and the arches. So this is just already suggesting there's some cool kind of geometry. There's some interesting interplay between, let me call it the local geometry, which is the bifurcations and terminations, and the global geometry, which is the overall fingerprint type. Not precise enough that I can articulate it and, you know, say something mathematical, but it does seem that by looking at a bunch of these by hand that there's some signal there. So again, the hope is that persistent homology will detect that signal. Okay, so this is just a representative sample where we can just use RIPs using, this is for unoriented, so we just used, I think, L2 norm for R2, and we just did the usual RIPs, persistent homology, computed the barcode. And you can't see much from this. The idea is if I did this for, you know, thousands of loops, thousands of whirls, thousands of arches, maybe they'd be more similar along within a given category than they are across. There's not much you can tell from this picture other than that these barcodes, as I said, they're complicated. This is not like the Klein bottle thing where you can actually see the 3-circle model. I can't tell how many loops there are, I can't tell what they mean, there's a ton of components. So there's lots and lots of information going on, it's really hard to see what's going on. This was now adding in the angular orientation of the minutia. And again, we get interesting looking barcodes, but don't ask me to interpret them. This is just showing that the actual FBI fingerprints have a lot of noise in the images that we're using. So we actually did a second approach that wasn't based on minutia. We were curious, can we also just use the image directly with persistent homology? And the first step we had to do is just by hand was crop these things because they have a lot of these are actually taken from real crime scenes in labs, so they have a lot of noise. Like one of them, I think, I can't see here, but one of them you can actually tell is on a dollar bill. I don't know what the backstory was. Okay, so here's the idea we had for the just using the JPEG directly rather than using the minutia. So I'll skip to the punchline. What's bad is this didn't work as well as the minutia. What's good is that you don't need to do really any pre-processing other than a little bit of cropping. it's very time-consuming for an expert to find 120 points on each fingerprint. There are automated methods for doing that, but they're not perfect and they take time. So we were curious, can't I just feed TDA a JPEG of a fingerprint and it just works with that? So we tried various ways of computing barcodes. The simplest one is, let's just consider the JPEG as a surface. So I'm just going to plot the grayscale intensity as a height, and now I have this very spiky mountain range. And one of the flavors of persistent homology is this sort of discrete Morse theoretic version where you kind of imagine the ceiling coming down and you chop off super level sets or sub-level sets, and you compute homology of those, you get persistent homology. So we use this Morse flavor of sub or super level sets. One was just directly on this, but one thing we realized is, well, the problem with the fingerprint is you basically have no level sets and then you have all the ridges. You're not really seeing the curvature of the ridges. So I wanted something that would detect kind of how the ridges are looping around and curling. So a little trick that we tried was just to slant the fingerprint. So it's a little bit easiest to see here. So we just multiplied this JPEG by the function x or the function y or some linear combination, and that'll just tilt the fingerprint up. If you think about what happens, now as you're bringing the ceiling down and taking these level sets, you're going to be picking up more and more of the individual ridges as they curve around. So it's just sort of a cheap way of, or an easy way of getting the actual geometry of the ridges, even though they're at the same height. Once you tilt it, you're actually walking kind of from left to right through, or from right to left through the image, rather than just all at once. So again, you can do this in lots of different ways. You can bend it in nonlinear ways. There's infinitely many things you could try. And these are just samples of things we tried in barcodes. Again, it looks like these are very, very complicated. There's hopefully enough signal in there, but can't really tell until you run the classifier. Okay, so we actually did this project several years ago. So I think our use of TDA is a little bit outdated. But again, our goal wasn't to be state-of-the-art. It was just to kind of see a little bit about what is persistent homology detecting. So very quickly, we wanted to coordinatize. We didn't know about several of the methods that have been discussed already today, like the templates for getting vectorizing coordinatizing. So one of the things we found, there was an early paper that Gunnar mentioned in his talk that came up again, is polynomial features. So these were some polynomial features that came up in that earlier paper of Gunnar's. Another thing we thought was to look at, I did this with, it was in collaboration with a statistician, Chul, who's now at Southern Methodist, and Chul said as a statistician, one of the first things you think about is summary statistics. So we thought, let's just throw these things in. You can look at various means, medians, standard deviations of starting points, ending points, and lengths of the intervals in the barcode. So a whole bunch of features. One could write down a ton more. Oh, the regression ones just means we looked at various things like I guess we just did the endpoints. So we looked at the endpoints and sorted those. That gives a curve. You can fit polynomials of various degrees to that curve and take the coefficients. That's another way of getting features. So don't think that this is done in any scientific or methodical way. We just really wrote down a bunch of random things that came to our head. And the result was, by tilting the JPEGs in different ways, by using different norms when combining the Euclidean plane with the circle to coordinatize our minutia points, by using these various features, we ended up with about 500 features. Roughly half of them are from just looking at the JPEG, and half of them are looking at minutia points. And we're just curious, how well do these perform? So we did very, very simple machine learning. We just used linear discriminant analysis, LDA. And the point wasn't so much what these numbers are. So as I said, state of the art is high 90s for a problem like this, but it's hard to say because this is a small data set. People normally train these things on larger data sets. But what was interesting to us is how the various features performed and competed relative to each other. So for instance, one kind of interesting thing was I kind of assumed that the connected components, the zero-dimensional homology, would be the main thing. I didn't think loops would be so relevant here. But it turned out if you only use zero-dimensional homology rather than only using one-dimensional, you actually get a significantly worse accuracy. So in other words, loops were better than connected components. And doing connected components together, meaning using zero and one-dimensional features, didn't perform any better than just using one homological dimensional features. After we wrote this up, we tried a little bit with two-dimensional, and there was some signal there, but it didn't really improve what we had before. The other thing that I found most interesting was So remember, the first idea for this project was fingerprint people view a fingerprint as a collection of minutia, which we can call a point cloud. And that was one of the first flavors of persistent homology, is rips on a point cloud. Well, it turns out it actually does terrible if you just feed the minutia as a point cloud directly. So this is what had 62%. So once you throw in the angle of the minutia, in other words, the orientation, that's when the accuracy jumped up drastically. But just using the unoriented minutia did significantly poorer. So the punchline for this was, again, not trying to be the best fingerprints, but just trying to see what is TDA seeing. And one thing we kind of took away from this is, even if you see data structures that look sort of like point clouds that you feel are geometric, that TDA might have some advantage to, if there's a little bit more geometric information, so for us, it was a point cloud with little arrows at each point, so an oriented point cloud, that extra structure could make the difference between this being fairly successful and fairly unsuccessful. That's sort of our good news, is use the more geometry you can find, use it. Don't just strip everything away to a point cloud. That's the optimistic part. The pessimistic is we still don't really have a sense for how or why this worked. So we just have tons of features, tons of ways of putting things into the pipeline. And again, I have no intuition for why one-dimensional worked better than zero-dimensional. The JPEG didn't work so great, but it wasn't terrible. So there is geometry in fingerprints, and TDA is picking it up, but it turned out to be more complicated than we expected.
Awesome. Thank you.
So we have time for 3 to 4 questions. Do you want to go first?
Yeah, cool stuff. So when you tilt, does that ruin the rotation variance of your?
Yeah, which can be good or bad. So if the FBI is frustrated that criminals are purposely rotating their fingerprint when they're getting tested, then this is bad because that's going to take away the advantage of TDA. But if you want to distinguish, if you trust the orientation and you want to distinguish from left and right, then you can use that deliberately. So it's just an extra layer you have to think about. Exactly.
Any more questions? Okay, no more questions. Let's thank our speaker.
Thank you.